Okay, so this is a lecture that we're going to talk about the quantum mechanical model of the atom. Basically, this just the ins and outs of it. Some of this will repeat one of the earlier lectures that I put up, because remember, they were what I had ready to go. So if you want to skip the part that's repetitive, that's great. I highly recommend listening to it at least a second time. I will probably break this up into 2 different lectures, okay? All right, so a lot of you guys have heard of Schrodinger's cat, okay? If you haven't, Schrodinger was a guy way back in the day. Schrodinger guy, listen to me. He was a scientist, just kidding. But he had this cat that he put in a box. And the idea is that you leave the cat in the box. It's kind of gruesome, sorry. And if you left it there for forever, you wouldn't know if that cat was dead or alive, save for opening the lid and looking. Okay. And in fact, that was a kind of joke going around during the height of COVID, Schrodinger's COVID, where it was like, oh, you don't know if you do or do not have the COVID unless you actually go ahead and take the test. So the idea behind that is that there's some things that we can't quantify, both position, energy, all these different parts. All right. Now, one thing I want to make very clear, this is not a history class. There are going to be some people from history that I expect you to know their name and what they did and contributed. But I don't expect you to know years. And sometimes I'll put that out there just to kind of give you an idea of what what we were dealing with at the time. So we discovered, well, I say we like I had something to do with it. It was discovered extremely small matter. All of the things that were extremely small, they were all discovered experimentally. So when we talk about these subatomic particles, we're talking about things like electrons, protons, neutrons, all these kinds of things. All right. This whole idea is that right here, where's my pen? Gotta get my pen settings. There we go. Okay. The whole idea, this is a big takeaway. Subatomic particles appeared to exist in 2 conditions. They had duality. Why do we matter? Why do we care about this? Wave matter duality. So how does that apply? When you have electrons and you get this, what we call particulate behavior, all right, meaning the behavior of the thing, then we could figure all that out only experimentally at the time. Only experimentally, okay? So they had mass and volume and took up space and size, but then they also had energy characteristics. That's where our wave duality comes in, okay? We should probably know by now that electrons, yes, are incredibly tiny pieces of matter. So this is an interesting just kind of way of thinking of it. The number of electrons in a single speck of dust is higher than the number of people who have ever lived on the earth ever. Okay, so a speck of dust compared to electrons, the amount of electrons in that speck of dust is a larger number than collectively every human who's ever lived on the earth ever. Okay, that's just to give a little perspective of how small these things are. We cannot directly observe them, meaning I can't hold an electron in my hand and look at it. It's clearly too small. We have to do everything experimentally and see what behavior is exhibited based on, how that works. All right, so when we look at what's happening, we know we have the periodic table. I'm sure you guys have seen it many times before. You may not quite understand it just yet, but by the end of the semester, you will be able to read it like a book. All right. And the periodic table, it's not like we threw elements up there and numbered them 1 through, let's see here, 200 and something. We've discovered a few new elements in the past couple of years. So it's not that we just randomly put them in order and said, oh, we like this one, so we like this one here, that one there, blah, 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 blah. What we've done is we have found that many compounds have trends. And the trends have to do with things like atomic radii, metallic characteristic, state of matter, how they form ions, meaning how they gain and lose electrons to become positively or negatively charged. And many of these elements are in what we call families, and they do kind of the same thing. So if you look at your periodic table and you look at the first column that starts with hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, okay? What we know is that even though those are all metals, they're going to bond with something else exactly the same. So what I mean by that is if I have a potassium and I have a sodium, they're in the same family. They behave similarly. When they become charged, they become a +1 charge. We'll get into charges and all that stuff later. If that potassium is going to bond with an oxygen, it's going to do it in a 2-to-1 ratio, forming K2O. Sodium, if bonding with oxygen, will do the exact same thing, a 2-to-1 ratio, forming Na2O. Okay, that is a common trend. You'll also notice that as you go down the periodic table, the atomic radii of those in the first column, they increase. So lithium is smaller than sodium, which is smaller than potassium, et cetera, et cetera. All right. So atomic properties that we can predict right here. Why are some elements metals and others non-metals? Why are some elements going to gain or lose electrons? Why do some elements, behave very reactively while others pretty much inert? Why in other periodic patterns do we see the properties of the elements, right? All of these questions can be answered with one thing. In chemistry, stability drives everything. You need to write that down. Stability drives everything. Okay? And because of stability, different elements will behave differently, doing these different things with these different characteristics that we just ask these questions of. And we're going to go through this semester and talk about all of these and figuring out why they do what they do. Okay? It's going to have to do with things like how many electrons they have, where are those electrons located, what makes something most reactive. For example, I kind of refer to fluorine as the bully on the playground. All right? It is very reactive and it wants to grab an electron. It needs one more electron to be stable. And once it gets that one more electron, it is good and it is not giving it up. All right? Meanwhile, if you go to YouTube, you will see and I used to do this as a demonstration, but my piece of solid sodium that I would use was maybe about the size of an eraser on a pencil. And I would put it into a 500 milliliter, or sometimes 600 milliliter beaker of water, and the whole thing would just explode. All right. If you go on YouTube and you look up sodium in the lake, you'll see a guy take a piece of sodium about the size of a brick and toss it into a huge lake, and the whole lake explodes. Okay, it's actually really cool to watch. I suggest going to YouTube and looking at that. Why? Because sodium in water is just as reactive as fluorine is if there's a nearby electron. And we're going to talk about all these reasons why. So light, we've always known that, and you guys are going to find I'm a fantastic drawer. So here's my beautiful light bulb. Yep, great light bulb, isn't it? Okay. and it gives off light. And for the most part, we know that light travels in a wave-like pattern, okay? What we're going to find out very soon is that yes, there is a wave-like pattern, but it is not a continuous string like I drew. What it is photon bursts that travel in a wave-like pattern. Okay, so we still get that wave-like pattern, but we're going to learn that it's not a continuous stream. They are photon bursts that are quantized. All right, so when we talk about light, we talk about it in terms of being electromagnetic radiation. So what does that mean? That means perpendicular and, perpendicular to each other, meaning you can think of like an X and Y plane. I'm not even going to attempt to draw this three-dimensionally. I'm pretty sure there's a picture coming up where the light oscillates or does that wave-like pattern. And it does it both on the X and Y planes perpendicular to each other. When they are, sometimes they'll be in sync and sometimes they'll be out of sync. So the electric field is where the charged particle experiences force. The magnetic field is where the magnetized particle experiences force. So we have electrically charged particles and magnetized particles. And that's where we get, ergo, electromagnetic waves. And the speed of light, I know you've seen this. They travel at this speed, 3.00 meters, or 3.00 times 10 to the 8 meters per second. And our variable that we use to describe the speed of light is a capital C. Some books you'll see it as a lowercase c. Just know that this is different than this, which is different than this, okay? This, which is also different from this. You're going to find, and you did hear me say this on another lecture, capitals, lowercases, and paying attention to detail is critically important. What I have here is the speed of light, right? I have specific heat for this one, centimeter, degree Celsius. Completely different things. Oh, also, this is also the elemental symbol for cesium. Yeah, so details are going to become very, very important in this course. Oh, here's the picture I was talking about. So again, three-dimensionally, if you could think of this as kind of your X and Y coordinates, right? You get this three-dimensional where you have the electric field and the magnetic field component. They're drawing the electric field in red and the magnetic field in blue. Again, it's described as a wave that is oscillating, meaning that up, down, and also turning left and right. They just think about the regular word oscillating. With this wavelength and this wave-like pattern, we get amplitude, wavelength, which we use a lambda, Greek letter lambda. And then do they also do, hold on, I'm looking for something. Yeah, they do. So frequency is the number of times we get a wave. Okay, so if I just drew mine, we're going to pretend that's all even and perfect, right, guys? All right, so if I'm doing peak to peak, this would have a frequency of 1, 2, 3. Okay, so wavelength, measure of the distance between peaks. Amplitude is the height of the wave. So wavelength and amplitude are independent properties, meaning how long it is and how high it is, they're not related. I could have two things that have the exact same amplitude and way different wavelengths, like I see here, okay? Way larger wavelength here than here, but relatively similar amplitude, okay? Wavelength is what determines color. So we talk about the visible light spectrum. Remember Roy G. Biv? The different colors are associated with different wavelengths. The amplitude and intensity determines the brightness. So what we're going to see is that, let me just draw this. Talk about a couple of things here. Yes, I'm on purpose getting wider. And again, we're going to pretend those are all even. Okay, I'm going to compare this one that I just drew to these two up here. You'll notice the amplitude on the dim one is very, very short, where on the higher one, we say bright, right? And that's because the higher it is, the more intensity it is, the more energy it has. If it has more energy, then it's going to be more bright. Now, what I drew shows very short wavelength going to a very longer wavelength. These short, high frequency wavelengths, and by short I mean wavelength, high frequency meaning many of them together, is the higher energy. Where the less frequent, longer wavelengths are the lower energy. Okay, think about it like you're at the beach. You've been to the beach on a day when the waves are just coming in like boom, 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 one at a time, one after another. They're pretty high. They're knocking you over. Okay, it's a yellow flag day. Those are coming in very quickly one after another, so not enough space between them. Short wavelength. And they're coming in pretty high and very quickly, one after the other, after the other, after the other. And those are knocking you over, higher energy. On those awesome days when it's a green flag day and it's, the waves are just kind of lapping in and they're short and they're slow and there's a lot of time between one wave and another. You take your chair and you sit down there because it's nice and it cools you off. Low, super low energy. It's not knocking you over. It's not knocking your chair over as you bring it to the water. It's just nice and easy. Okay, so we did talk about frequency and what it means. The units for that are hertz or cycles per second. Now I want you to remember right? We just got to remember that. If I had 1 over x squared, it would be the same as x to the 2 minus. You're going to see it written underneath the fraction sign sometimes. Sometimes you're going to see it like this, okay? But what you need to know, the takeaway is this, all right? So total energy is directly proportional to the amplitude and the frequency. So the bigger the amplitude, the more force it has. We just talked about that. The more frequently it hits, the more back to back to back to back, the more energy it's going to have. Here's our relationship between frequency, wavelength, and the speed of light. By the way, all these equations that we're going to go through in these chapters, these are all in that Tro constants and equations helpful cheat sheet that I, had you guys, told you guys to print out. It would be a good idea. Okay, so mathematically we can say this, but literally we're going to be, for the most part, plugging and chugging with these types of problems. All right, so here's an example. Calculate the wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the minus 14 seconds. Okay, so we're literally using the speed of light, which is our constant. The only constants you have to memorize in here are the ones for water. The temperature, boiling point and melting point temperatures, the specific heat, the density, all that kind of stuff. All these constants, the only ones you have to memorize are going to be for water. All the rest I'll give you. So you got your constant, the speed of light. You got the frequency. It says frequency. That's how we know to plug it in to this. And then they've rearranged the equation first. I don't care how you do it, what math works good in your brain. If you want to plug the numbers in and then rearrange, that's fine. If you like to rearrange first and then plug the numbers in, that's fine also. So do the math and boom, there we go. Now, I want to talk about something. I want to talk about these units. That is really meters per 1 second. Okay? So this is just seconds on the bottom. Why? Because that's what it tells us our unit is. So this one is really number 4.62 times 10 to the 14, no unit over second. So when I divide these, hold on, let me just not erase this. Oh no, what just happened? There we go. Okay, so when I divide these, this was 3.0 times 10 to the 8. When I divide these, how do those seconds divide out? Well, I'm going to look at this a different way. I'm going to say, okay, meter per second divided by number over second. All right? What was my rule in middle school when I learned how to divide fractions? Keep, change, flip. Flip and change, right? Flip and multiply. So if I say this, right? That's how they wind up canceling. This format of division is this, just written differently. That's how those seconds cancel out. Okay, now I want to explain something about this electromagnetic spectrum. If you could take Roy G. Biv, right here, if you could squeeze it together, it would fit right here in between infrared and ultraviolet. The only visible light is in this visible light spectrum. The rest of them are invisible to the human eye, but are part of the electromagnetic spectrum. So your lowest energy with your lowest frequency and your longest wavelength is going to be over here on this side. Highest frequency, highest wavelength, or shortest wavelength, highest energy is going to be over here. So if I were to ask you what has more energy, a green color of visible light or ultraviolet, and I ask which has more energy, don't look at this and say, oh, it's over here, so it's closer to higher energy, so it must be a green wavelength. No, because remember, this whole thing is fitting right in there. Okay, so it's actually before ultraviolet, so ultraviolet would have a higher energy than the green. Okay, I do recommend going through the PowerPoints and going through these conceptual connections. In your textbook, the answers to these, I believe they're at the end of the chapter, not the end of the book. But I do recommend going through these because these are conceptual connections, and you will see conceptual type problems being asked on your exam. All right, constructive interference and destructive interference. So constructive just means that the waves are in sync. All right, and when they're in sync, they come together to form a much higher amplitude and higher frequency, increased frequency. When they're out of phase or not in sync, they get destructive interference, which just causes a straight line. It's kind of like they negate, the wave of A negates the wave of B, so they just form a straight line. Okay, photoelectric effect. This has to do with wave theory, and it has to do with the electrons being emitted from a metal surface. And they emit from a metal surface and convert to light energy. The light energy is transferred to the electrons. So that's classic wave theory. Classic, words are hard today, y'all. Classic theory states that if the wavelength of light is made shorter or the light's wave intensity is made brighter, more electrons should be ejected. This should just make sense. If I'm getting shorter, more frequent, it's going to be more intense, it's going to be brighter, it should make sense that more electrons would be emitted. And then energy of a wave directly proportional to its amplitude and frequency. We've already talked about that. Okay, I'm going to stop here for this lecture. I'm going to put up a part 2, and then I'll put up another mini quiz, okay?